Each group will be given a different line encoding scheme. Those schemes that we just looked at, that's why I looked at that. Each team will be given a different line encoding scheme because we want to see for that given channel how the different schemes will perform, which scheme is a better scheme to minimize error. So it's kind of like a contest you have. Of course, you will get to pick your scheme because I will randomly assign your scheme to you, but you will actually take each bit. So let's say you get a bit 0. You have to know, based on your scheme, how do you represent 0 as a wave, as a voltage? All right, so what's going to come out for each of these billion bits is a billion symbols based on your line coding scheme. We're gonna, once you generate, so let's say these 3 bits came out and they're going this way, right? So the first symbol, second symbol, third symbol. The symbol that corresponds to the 0 based on, let's say, unipolar NRZ is that 0 will be 0 volts. 1 will be 5 volts. This one will also be 5 volts. So that's the symbols that will come. So if you want to think about it, this is step 1. Generate your bits. This is step 1 here, right? Step 2, you find a way in MATLAB to convert all of your binary symbols to voltage symbols based on your scheme. It's not going to be NRZ. It's not going to be unipolar NRZ for all of you. Now, the next step is to simulate transmission. So what happens when you transmit? Let's say you have a wire.
Nice.
If you put up, sorry, please repeat that.
So if it's simulated, it means that you could add stuff to it and stuff like that. Like
all right. So let's say we put up 5 volts. Let's pretend that we put a 0 volts, but let's ignore the 0 volts because there's not much action in the 0 volt. This is your wire, right? So you, at the edge of the wire that your system is connected to, that your transmitter is connected to, you put 5 volts on the wire. What's going to happen if you have a voltmeter at this end of the wire? After some time, the voltage that you put at this end, because you have a voltmeter here too, you will measure 4 or 5 volts, and very quickly, I think you did transmission line and the Smith chart. Did you do a course with Smith chart sometime back?
No, sir. We now start power systems.
No, sir. No, sir. Smith chart. Sir, the Smith chart thing is supposed to do this semester because we didn't do it to the other telecoms.
Let me just see if they changed that. See what's going on here. I'm worried for you guys. Did they call the Smith chart though in this? Let me just go chart. See, they call it something else by chance. Oh no, I'm doing my own thing. Control find. Let's just do chart and see how many charts you have in this course.
Sir, wrong string, sir. Wrong string. Delete 32.
Oh shucks. Let's see which course is the first course you was to Smith chart. Oh, field theory. Oh, okay. So they moved it to this course as the first course. Interesting.
Sir, so we're doing field theory till the 4th year.
What?
Yeah, sir.
Who's the genius? Who's the genius? You need this for 4116. You need this for my course. Oh my.
Sorry, don't have a lecture, sir. Unless you want to teach it, sir.
And I am. If they had told me early on, I could have. Damn. All right, it is what it is. When I was a student, those Smith charts came in either second year or first year. We got introduced because this is really a telecoms course. I know they're not calling it telecoms, But this is, someone told me that you don't do any second year telecoms course. The topics
Yes,
that were
sir.
in that course, or you
No,
don't
no,
do first year.
we
You don't
do
do
a
first
second
year.
year. We do a second year telecoms 2116.
Okay, so what you're doing in second year now, you used to do in first year, and this used to be a second year. These topics used to be second year. So when you come into third year and I say we have a wireless channel, you already know about propagation of waves. You already know about transmission lines. Because I'm about to give you a transmission line discussion here, but I have to tell you all you need to know. So when you put this voltage at this end of the wire, this end of the wire, depending on the frequency that you're setting the symbol at, and you notice you have something called skin effect here. When you send signals or voltage along a wire at high frequencies, the symbols or the signal doesn't travel in the center of the transmission line. It travels on the skin. That's why if you look at the most popular transmission line for communication, it's called, one second. Where's my mouse? It's a cable. It's a coaxial cable, but it's a special type of cable we call a feeder cable, where the entire center is missing, because we recognize that skin effect is a thing. Skin effect we learn in telecoms, but in the industry, the guys don't give you. So telecoms cable, they're very, very light. Unlike power cables, so this is a typical cable we use for high-speed communication. Oh, I don't want to purchase one. I just wanted a good image. Okay, they're trying to sell me something. We'll look at this one here. So if you notice what's happening, where's my mouse? We're looking on the right side of the screen, right? You have a copper, a thin piece of copper here, and you have a very thin piece of copper here in the center. Here you have a dielectric. So if you need to put a 5 volts on that, you would put your negative terminal or your negative terminal of your battery. Let's say you had a 5-volt battery, you were switching it on and off. When you see a binary 1 comes, you will connect this switch. So let's say we had a switch, we had a battery. Let's put a battery, 5-volt battery, and then a switch. So what we'll do, we'll take the negative terminal and put it, we can do it anyway. Let's put it to the minus. Who cares? We're going to put it this way because it's easier to put it this way here. The negative will go on the outside. That's not how you have to do it, right? You can do it any way you want. Now you put a switch somewhere. Let's get a switch. I will open and close this switch depending on if I get a 1 or a 0. And this one will go to the other conductor. So I have two conductors. One is going to be at 0 volts, and one's going to be at 5 volts. Of course, I'm going to ground somewhere, but this is going to be 5 volts. When I want to send a 1, I just close the switch, and these two ends or these two edges become energized. It's going to take some time for that voltage, that voltage signal to travel down the transmission line. And in I guess they call it 3116 or 3118 or whatever it is. In that course, you will learn what factors affect the speed. Let's see where we see speed. Wave velocity. So we can actually predict quite accurately how fast that pulse will take to travel down that transmission line. Let's leave that alone. Let's move away from that. I'll make sure I don't hold you responsible for knowledge from 3208. I wonder what you did in 3108 though. Let me see what you did in 3108. You guys can tell me too, What did you do in 3108?
Sir, we were supposed to do. We didn't do it.
Wait, you didn't do 3. Which one is it you're not doing? You didn't do
Both.
3108 and you're
Both.
not doing you know how to teach this course. You guys are in trouble.
So what is
we don't have
pressure,
lecture,
sir?
sir.
Please repeat that.
We don't have a lecture for the course.
It's pressure,
Who
sir.
normally teaches it? Any idea who normally teaches it?
Is Shazzy my name?
Okay.
Ibrahim,
Okay.
sir. Some Shaz Ibrahim, some madness, sir.
Okay. Damn. You guys are. Now this course is easy because you have a math course that is almost the same as this. It's just that this course goes a bit deeper into the theory. Yeah. So all the things that you will need for the wireless, you guys have not touched. All right, it is what it is. Life goes on. Anywho, the point I'm making is that I lost too much of what I wrote. Let's see what I can bring back. Yeah. You're gonna send the 5 volts at this end, and the way it will go over physically is that after some time, it will travel down. But what's gonna happen at the far end is when you receive that signal, because initially there was 0 volts at this end, there will also be 0 volts at this end. If you look at your voltmeter, you will see 0 volts all the time. When you close the switch, you will see 5 volts on this voltmeter here. And after a little while, maybe not significant amount of time, you will see a voltage on this end. What voltage would you see on this end, guys? Without even doing that transmission line course, you're going to be affected by noise, attenuation, but attenuation will be the major one that will affect you. There'll be some noise. There might even be interference. The major channel impairment of this simple experiment is that as the signal travels down, put it this way, the symbol that you send is a 5 volt symbol. What is the energy of that symbol? If we know the time, energy is equal to power times time, right? We're trying to use physics to argue this because you don't have that 3108 and 3208 to back you up. So energy is power times time. Let's say we know the time. Let's say the duration of this is just 1 second. That's ridiculously long, but let's take a second just because we don't want to use no fancy number. So we know what is the time. How do you find power if you know voltage? Well, power is V squared upon R, right? So if I want to know the energy of this symbol, I just have to pass this voltage across a 1 ohm resistor because I want to make my life easy. So the voltage is 5. It's going to be 5 square. It's 5 square volts. It's delivered across a 1 ohm resistor. I want to let it have no effect. And let's say it is a 1 second duration symbol. So the energy is sort of going to be 25 whatever units of energy you have. We can say joules just because I want to have it as joules, but I mean, it doesn't have to be joules. The point is, we want to sometimes use voltage as a measure, as a surrogate for energy. We're allowed to do that if we let R be normalized to 1 and let T be normalized to 1. All right, but the point is, when I put this 5 volt pulse, I'm putting 25 units of energy on this wire. Now, you know that as the energy is traveling down the wire, some of it will be absorbed by the atoms and the molecules that makes up the transmission line. In fact, if you the laws of physics will allow, if the frequency is high enough, will allow the signal to travel on the outskirts to minimize how much energy will be lost. So when you come, let's say here, you're not going to find 5 volts. Because of attenuation, you're going to lose some of that energy as heat, and maybe even sound. The voltage will probably be a 4.8. So when I do my V squared upon R times T, you're not going to get the 25 units of energy. You're going to get less. And the point is, when you get down to here, you might get 4.5 if the cable is long enough. The point is, you're seeing that when I send a 5 volt in real life, because of attenuation, I'm likely not going to get not going to get 5 volts. I'm going to probably get 4.5. That's in real life. Let's come back to MATLAB. When you finish step 2, you had a 5 volt symbol. When you send that in MATLAB, what do you expect to get? Something less than 5, right?
Yes, sir.
Great. But because we're not doing attenuation or as a channel impairment in MATLAB, I'm going to allow you to pretend once you do step 2, whatever you get in step 2 is what you transmit. So here's the transmitter. Let me clear up a little bit. I could allow you to do attenuation, but that just gives you more work to do, and I want you to get over lab 1 pretty quickly. All right, so I take the attenuation out. That's why your simulation of transmission is not going to take any effort from you, because I'm going to assume that your transmission line is so short, and again, this is something that comes out of 3208. If you have a very short transmission line, attenuation is going to be insignificant, provided that other, like your inductance, your capacitance, your resistance are well designed for your transmission line. I'm just going to do 2 wires now for the transmission line. Our assumption is that if you put 5 volts here, the 5 volt will show up at the far end. So this is your transmitter side, your TX side. And this is your RX side, your receive side. So when I say send that symbol, the 5 volt you send will show up as a 5 volt on the other side. So you don't have to do anything. It means that whatever you have as your transmit symbol here as 5 volts will also be your receive symbol. In a real life situation, it's not going to be 5 volts, it might be 4.5. So you will have to go in MATLAB and find a way to statistically model the performance of that transmitter channel, so that whatever attenuation is typical of that channel, based on the length of the channel, that is what statistically you'll see. So sometimes you might see 4.8, sometimes you might see 4.7, but we're not doing that. We're going to assume that what you transmit is what you will receive, or what will come to your receiver. All right, so let's go back to the Moodle page where I was showing you the steps in your lab 1, because I want you to start thinking about it. So first step, remember, generate your bit. Step 2, convert every binary digit, every logical symbol, zeros and 1, to a physical symbol, maybe 0 and 5 volts. That's step 2. Step 3 is transmit. Now, in a real world, you have to model attenuation and maybe even other channel impairment like distortion. But we can assume that attenuation, distortion, those guys, and interference are negligible. So step 3 says whatever symbol, if you have a 5 volt here, you will have a 5 volt on the steps of your receiver. This is the transmitter here. This is the front end of the transmitter. We call it FE. And this is the back end of your transmitter. So transmission happens from the back end of your transmitter to the front end of your receiver. Oops, front end of your receiver. This is your front end of your receiver. So if you have no attenuation, no distortion, no interference, whatever you send will show up on from the back end of your transmitter, will show up on the front end of your receiver. So step 3 requires no action from you. So I hope you've seen it. Step 1, step 2, step 3. When step 3 is over, you have the 5 volt sitting on the front end of your receiver. Step 4 says decode. I should change the color here. Because I want some of you to start over the weekend thinking about your assignment, right? So step 1, step 2, step 3, no action from you. Step 3 is a given. Whatever you transmit your symbol as, assume your transmit symbol is your receive symbol. Step 4 is that you add noise. Because remember, noise comes in at the receiver. So when you send your 5 volts here, we're assuming that the 5 volts gets across the transmission line. And remember, the transmission line terminates on your receiver. So the minute the symbol or the energy goes into the receiver, it will be impacted by noise, additive wide Gaussian noise. So step 4 is for you to add noise to the process. I hope you're writing down something, guys. Step 1, generate your bits. Step 2, use your appropriate line coding scheme and encode the bits to physical symbols, voltage levels. Step 3, assume that there is no attenuation, interference, and distortion. So assume that whatever your transmitter backend produce, your receiver front end receives. That's step 3. It's done for you.
Sorry, talking too fast, sir. I can't write down everything is
No, I thought you wrote it down already. I was just recapping.
Yeah, this was
all right. And now you write it down. All right. Step 1, I might say differently. Generate bits. Random bits. I should say random because it has to be random.
You say it was
bits.
1,000 or a million?
A billion. But
billion.
When you start in your code, I would advise you not to do billion because let's say it takes some time to generate a billion. You'd be sitting there waiting when you should be coding. So do 10 bits to start. And MATLAB will generate that quickly. Write your code for encoding. Step 2. MATLAB will encode that quickly. You see, if you had a billion bits there and you ask MATLAB to encode, maybe your system is not so high-end. And you'll be waiting an hour for MATLAB to encode. So don't start your code. Maybe write your code in such a way where you say N, create an input state, use the input MATLAB input keyword, and ask the user when they click run your code, ask the user for how many bits they want. And you just put in 10 to start out. Or maybe don't even ask the user. Leave that for the last, like bells and whistles. Just hard code it to 10 bits as your first line of code, if you will. So you just generate 10 codes and you run through the program for 10 codes, for 10 bits. So you take your first bit, encodes it. Encoding using your appropriate or the assigned line coding scheme to your group. Each group will be assigned one. Encode based on that. Step 3, you have to do nothing. Why? But it's important you understand why you're doing nothing. In real life, you do something. You cater for attenuation, you cater for interference, and you cater for distortion. I'm assuming that these effects are negligible. So that's why you're doing nothing. Remember, it's 4 impairments. We assume 3 are negligible. Step 4, you deal with the 4th one. You add noise to your receive symbol. So we send 5 volts out. Let's say we generate a binary 1. Let me change the color for that. We generate a binary 1. Step 2 takes the 1 and makes it into 5 volts, a 5 volt symbol. Step 3, I put the 5 volts on this wire, and it turns out to be 5 volts over here. So I did nothing fancy. If attenuation was involved, I might have gotten 4.8 volts. You will have to model that statistically in MATLAB, but we're not doing that. Step 4, you have to take your receive symbol and add noise to it. Now, noise is a statistical process. So maybe at this instant in time, when that 5 volts shows up on the doorstep of your receiver, the noise on the system, the noise of the receiver is only 0.1. So the 5 volts you receive turns into 5.1 volts. You're lucky it's only 0.1. So step 4 gives you 5.1 volts as your receive signal level. If you're unlucky, the noise could have been minus 3 volts because the noise follows the Gaussian distribution. And the Gaussian distribution goes from minus infinity to positive infinity. Of course, the probability, this is the probability, the height of this distribution is probabilities, right? And this is voltage levels. Voltage levels goes horizontally. And the height of the graph tells you the probability. So because minus infinity has a very low probability, I don't expect the noise to be minus infinity ever. Because minus infinity don't even exist. Maybe minus 10 doesn't even, minus 10 will have a very low probability. That's why I'm not saying the voltage is minus, the noise is minus 10. But minus 0.1 would probably be somewhere here. And that has a reasonably high probability. In fact, 0 has the highest probability. So more often you might have 0 noise than anything. But sometimes you will have plus 5 volts noise or minus 5 volts noise. Any noise is possible from minus infinity to positive infinity. The extreme values are very unlikely, but additive wide Gaussian noise has this sort of statistical property. Point is, step 4, you add your AWGN noise to whatever symbol you receive on your transmission line. All right, so we go with step 1 to 4.
AWGM noise?
Yep, additive wide Gaussian noise, AWGN. If you just Google that, you'll get tons and tons on this. AWGN noise. This is a statistical process that produces noise, and it is going to ensure that your system, when you size your system and test it according to AWGN, when you cry it into the field, you guarantee that the performance in the field will not be much different from what your test performance was if you use AWGN noise as your test. So step 4, you add noise to the 5 volts. In this case, we added 0.1 volt. So our symbol now is now at 5.1 volt. Step 5, we undo step 2. That is, we decode. Remember, step 2 was line encoding. Step 5, let me change back my color, is line decoding. Because remember, line encoding took symbols, logical symbols, zeros and ones, and converted to volts. That's what step 2 did. That's line encoding. After step 4, you have 5.1 volts. What are you going to do with that? You have to move from volts to ones or zeros. So you have to write a piece of code to work with the voltage you receive and convert it to either 1 or 0 based on whether you think 5.1 should represent a 1 or a 0. More on this later. We're wrapping up. So step 5 is to do line decoding. Once you decode, the voltage will turn into a bit. So you got a receive bit now. Either 0 or 1. In this case, I think you'll get a 1. But you might get a 0 depending on the noise that was added to the system. And we'll talk about how you'll get it later. So step 5 produce for me a receive bit. Remember at the transmitter, this is MATLAB you're in, right? Not the real world. In MATLAB, you will have in a memory location the bit that you actually send. The fact that you were sending a 1. In MATLAB, you'll have this stored as a binary 1 somewhere. That's your transmit bit number 1. Also, in MATLAB, you will have a storage location called receive bits, where the first bit position will have whatever you just received. So you receive the first bit as 1. So you have that stored, you send a 1, you receive a 1. Of course, you'll have to have a register that stores a billion bits eventually. But we're just doing it for the first bit. Your next step, step 6, is to do a bit-by-bit comparison. So let's pretend that we had 3 transmissions already. When we send a 0, the 0 will still show up as a 1 for whatever reason. When we send not a 0, it showed up as a 0. So what we'll have to do now in step 6 is a bit-by-bit comparison. We'll take bit 1 from the transmit register, compare to bit 1 with the receive register. Compare bit 2 from transmit to bit 2 with the receive. Bit 3 with bit 3 with the receive. All right, so you do a bit by bit comparison, and you will note the number of errors.
Sir, can plot it.
So eventually, yes, so eventually you will plot, because what will happen, I didn't tell you this, I should tell you now. When you generate AWGN noise in MATLAB, MATLAB will ask you for, before you even generate it, will ask you for the signal to noise ratio that you want. We'll talk about this a bit later. But MATLAB will ask you for the signal to noise ratio that you want the noise to be generated at. So in the program, in the lab, you will be testing your system from minus 20 dBs of signal to noise ratio all the way to positive 20 dB.
So I mean, what is signal to noise ratio in terms of generating noise? Aren't you like controlling the signal to noise ratio when you add the noise to the signal? Because I can't recall seeing that in MATLAB.
They're different function. They're different. You see, you can use MATLAB as inbuilt function, while MATLAB can allow you to use a built function. So if you're using a MATLAB built-in function, then the approach might be different. See, I'm explaining the process, not necessarily explaining MATLAB functions. You can use MATLAB functions, or you can actually take your received signal, your 5 volt, figure out what the additive void Gaussian noise is at this signal to noise ratio and add it to this guy. Or as you're saying, I'm not saying you can't do this, you can take the AWGN function in MATLAB and it has the structure. But just make sure whichever method you use, for every simulation, you have to note in a register somewhere that this has been done, for example, minus 20 dBs. So when you plot your graph, you know that your bit error rate that you find, I know I'm rushing it, we're finished here, but guys, when I come back the next time, we will continue this discussion from step 6, right? Remind me that step 6 is where I need to continue the discussion from. But at least you can start step 1, step 2, step 3. Over the weekend, what I will do is assign, well, you guys have to tell me your group IDs. Give me your group participants so I can assign you to groups. But then what I'll do tonight is that I will let you know which line coding scheme group 1 will deal with, which line coding scheme group 2 will deal with. The first group that gives me their group members will be group 1. The second group will be group 2, and I'll populate that on Moodle so you'll know what's up. But if you start thinking about your lab.
So in order to avoid confusion and so on, we actually created a document for the first assignment, because remember you had some problems with the grouping on Moodle, right? So we actually created a shared spreadsheet, and we allowed persons to group up as they please. So I don't know if that was gonna work, or if you need some
freestyle, because if person don't join a group, then we wouldn't have a group. So what you guys can do, I want the class rep to have a stick and police persons to. So you'll check. I'll give you the task of making sure that everyone's in a group, right? Because if I do that, somebody might decide that they don't want to go in a group with this guy, and they don't have a group yet, and then I can't start the assignment because everyone is not in a group. So it's either I generate the groups, or you select your groups by a certain time. So we can use the Google Docs or whatever you're using, but you need to police it and make sure everyone is in the group by the next class.
Yes, sir. I'm one of the class reps.
Before, yeah.
So, sorry. And how many groups are you looking for?
It wasn't a number of group. I think it was a number of persons in a group. We discussed. What was it we discussed? What's the class size? Class size is 21.
23, sir.
23 active persons, or 23
yes, 23 active.
All right.
The courses, yeah. Let's
do 4 persons in a group. Let's do 4 groups. No, let's do 5 groups. Let's do 5 groups. I don't want to have too many persons in a group. Let's do 5 groups. So 5 groups. 5, 5, 25. So, yeah, let's do 5 groups. We can expect 4 in a group, 4 or 5. Some groups will have 5, of course, but 5 groups we want. So 4, maximum 5 in a group. All right, but what I'll do, I'll commit for this weekend. I'll actually put up so I'll say group 1, Actually, I want you to give me the groups first because I want to randomly assign these different line coding schemes. Because some schemes are easier than others. So I don't want to favor any group. I want you to create your groups, have it up there, and then I'll randomly I'll do the pick a wheel thing, and I'll spin the wheel the first time. Whichever number it gets, I'll put that into the group. All right. So I look out for
Yes,
that.
sir.
Communicate with me. All right, guys. Let's call it tonight. My headache is
Yeah,
coming
yeah.
back.
All right, cool, sir. Good, good.
Uh-huh.
Sir, you don't know, sir.
All right.
Take it
Look
later,
at it.
yeah?
Yeah.